All right, so this is our second lecture on heat exchangers. And last time we talked about different types. What are just some terminologies about different types of heat exchangers? Crossflow, a shell and tube, tube within a tube, double-walled or concentric tube. So concentric tube is good to know because we analyze that to death. Crossflow and shell and tube, we use the structure that we developed for those parallel or concentric tube. You also had counterflow and parallel flow in the concentric tube. There's others out there, plate heat exchangers, which are common, but this is an introductory class. Talked about the overall heat transfer coefficient U. And last time I think we talked a little bit about the log mean temperature difference, but I'll emphasize it today. So let's refresh our memory. We have a concentric tube. I usually sketch it something like this and put the hot fluid and the cold fluid flowing. Hot typically above for me, but the syntax or the notation is not that important. And for counterflow, the hot will flow, let's say, left to right, and the cooler fluid would flow from right to left. And we talk about the temperature of the hot in, the temperature of the hot out, the temperature of the cold in, and the temperature of the cold out. A lot of times we'll plot on a temperature location diagram X going from 0 to L. It will plot the high temperature fluid, maybe doing something like this from inlet to outlet, flowing that way, and the cooler fluid flowing, maybe I'll draw it down here, lower the temperature, and going like that. Okay? So what was this temperature difference right here? Would talk about a delta T on that end, delta T2. That's going to be the temperature of the hot out minus temperature of the cold in. And this delta T right here, we'll talk about delta T on that end, delta T1 is equal to the temperature hot in minus temperature cold out. All right. And what we do is we have 6 equations I want you to become very familiar with. 3 are differential and 3 are global macroscopic equations. So let's take a look at the differential. So we focus on a small little element dx. And in that heat exchanger at that location we have one TH. It's between TH in and TH out. And we have one temperature cold. And then what we have is we have a dq, the amount of heat transfer, the small amount of heat transfer over that length or that area of that heat exchanger from the hot to the cold. So we could say, well, the amount of heat transfer, the small amount, is equal to the mass flow rate of the hot fluid, the specific heat of the hot fluid, times, and this is where it gets a little tricky, but we have the negative of the rate of change of the hot fluid temperature with respect to x, because look at the profile. It's decreasing in increasing x. Isn't it a negative slope? So I want to talk about not a negative delta T. I want to talk about a positive change in the hot temperature fluid. And so we multiply by delta x, and that gives us the positive. This is a positive small amount of heat transferred out of the hot fluid. I emphasized this last time, did I not? This is a little bit of review. And then you write the same equation, dq is equal to m dot c sub p of the cold fluid. Then we have dt cold dx, and then we have a delta x. So I leave a little space. Do I need a negative sign there? Or do I not need a negative sign? Take a look at the temperature profile. If I move in the direction of increasing x, does the cold temperature fluid increase or decrease? It goes down. But this always gives me a little conceptual, I've got to go slow here. My mind goes, I have to go slow. I know where the slippery spot, where it's difficult for my mind to grasp this. Because the fluid is flowing backwards. But I have an x-coordinate system that's always going to be going from left to right, the positive x direction. So once I've introduced that x-coordinate system, don't use an x-coordinate system for the hot fluid flowing left to right and then turn it around and put a different x-coordinate system going from left to right or right to left. Don't switch it. Okay? So that's why there's a negative sign right there. Professor, you didn't have a negative sign there last time. Did I talk about the counterflow last time or the parallel flow last time? So we'll talk about the small amount of heat transfer from the perspective, the first two were from the perspective of energy balances, out of the hot into the cold. Here it's a rate equation. It's going to be the local overall heat transfer coefficient times the amount of area, the small area, which we represent as P dx. Y, what's P? Perimeter. Dx gives us an area, times the local hot minus the local cold. So energy balance, rate equation. You also write it. So each one of these are the same. They're not, one is not a negative dq in one of the equations. I emphasized that last time. Same, true here. It's always a positive small amount of heat transfer, rate of heat transfer. Now, we have a similar equation. We say the total rate of heat transfer from the perspective of the hot fluid is going to be the temperature hot in minus temperature hot out. And I'm tired of writing m dot c sub p, so what do I substitute? Instead of m dot c sub p, cap c, and cap c for the hot fluid. The name of cap c for the hot fluid is heat capacity rate. And I didn't make up that name, but that's the name, and it's used throughout the literature. All right, and then Q, the heat capacity rate of the cold fluid times the temperature, and this is where I have to go slow. I have the cold temperature fluid, but which one's higher? Which one's higher? I want a positive Q, so I better put the temperature cold out minus temperature cold in. Do you see that? And it's like, hold it, they just switch space, locations. Which one goes first? You always want to talk about a positive Q. And the Q is positive out of the hot, and it's positive into the cold. All right. And now we're going to have this equation, Q is equal to UA. It looks just like this rate equation, but it's an overall rate equation, not a differential rate equation. And the appropriate average temperature difference is the log mean. That's right, the log mean temperature difference. That's the name of it. And the log mean temperature difference is delta T on one end, hey, that one right there, minus delta T on the other end, that one right there, divided by the natural log of delta T1 over delta T2. Quick question, not a clicker question. What are the units of delta T? Is it degree C or dimensionless? Delta degree C. What are the units on log mean delta T? Degree C, not dimensionless. It's degree C, isn't it? It's dimensionless in the denominator. Exactly. Well stated. Okay, so these are our 6 main equations. And what we do now is I want to derive this result for this problem. And instead of acting like it's never been derived before and starting with a clean sheet of paper and spending 20 minutes on it and then making 3 errors, have the students raise their hand and say, Professor, is that a minus sign? Oh, yes, it is. Did you leave it? Yes, it is. Oops. So anyway, I wrote it out. Let me kind of go through it. What you do is you have a small dx, just like this, and you have the heat capacity rates defined. We have that energy balance 1, differential energy balance 2 is differential energy balance. You agree with those, hopefully? No, there's no mistakes that you see. And then 3, and then what I'm going to do is I'm going to combine equation 1 and 3, and by combining 1 and 3, I get this new equation. And then by combining equation 2 and 3, I get another equation. All right, I cut you off. Where's my error?
The flow diagram. Your cold in is the wrong way.
Yep, sure is. Look at that. Cold is exiting on both ends. Oh, this is great. Thank you. You're awake. That's kind of a novelty for you, isn't it? Being awake?
It's rare.
It's rare. You didn't have to work last night. All right. Any other errors? I appreciate the feedback if you have one. Catch me. This is algebraic gymnastics, combining those two equations to get a new equation. Now I have one equation, and then it starts to look like a differential equation. I go back to an overall energy balance for both the hot fluid and cold fluid. I'm trying to get something to substitute for 1 over that heat capacity rate, and then 1 over the heat capacity rate. Then another few steps of algebra, and I move from this equation to this equation right here. Now it's starting to look like what I need it to look like. It's just a lot of algebra and what we call experience or insight. Yeah, you had to have done it before, and then you know what to do and how to do it efficiently. So I separate and integrate because I do have a derivative with respect to x. Put dx over here and bring this dt, where that's temperature hot minus temperature cold, over underneath. Then I integrate, and I get an equation where it's the L is the length, the integral 0 to L. And then when I integrate this delta t, I get the natural log. Substitute for the limits. At 0, that's at 0, it's delta t1. At the other end, it's delta t2. And I'm pretty well there, but I flip this around. I get Q is equal to, and then I have UA. A is P times L. And I get the log mean temperature difference. Delta T2 minus delta T1 divided by natural log delta T2 over delta T1. It's the same if you switched 1 and 2, right? The location, I covered that before. So QED, Latin for what I tried to say I was going to demonstrate, I've now demonstrated, right? So congratulations. It's in the textbook as well. Here's a little trivia. Somebody says, I have a problem, and it just happens to be that the hot is cooling down at the same rate that the cold is warming up, and the slope of those two lines are exactly the same. And so the delta T on one end, the delta T1 and the delta T2 are exactly the same. So if delta T1 equals delta T2, what happens to the log mean temperature difference? We get something minus something, the same thing. So it's 0 in the numerator, but we get the natural log of 1 in the denominator. What's the natural log of 1? So we have 0 over 0, and we run the calculus, and we say, I remember L'Hospital's rule, or L'Hopital's. Different books call it by different names. How did you learn it? I'm always curious. The Hospital? No L'Hospital? All right, well, the Hospital's rule. So it says take your numerator, differentiate it, take your denominator, differentiate it, and retry the limit. So that's what you do. So what I did was I said, let delta T1 equal to delta T plus epsilon, delta T2 equal delta T. Now I have something in terms of epsilon. Epsilon I'm trying to let go to 0. I check it. Yeah, it doesn't work. I apply L'Hopital's rule. Derivative of epsilon gives me 1. Derivative, this is where we have to work a little bit, of 1 plus epsilon over delta T gives me that. Now I can try that limit again, and sure enough, you get that the average, the appropriate average delta T for that heat exchanger is, guess what? Delta T. So our log mean temperature difference makes sense. So here's a problem right here. And I have some questions ready to go for this problem. As shown, can you tell me if this problem, first of all, which end is the hot fluid coming in at? Can you tell? So this is the temperature hot end. This is the temperature hot out. Which end is the cold coming in at? You're right. Temperature cold in is over here. Temperature cold out is over there. How did you make that deduction? It goes slow. You have to look at it. But you see that hot is cooling off and the cold is warming up. That's what's going to happen in a heat exchanger. Can you tell if this one is either counterflow or parallel flow? You want a clicker question? Yeah, let me give some easy clicker questions here. So, is this counterflow? Answer A. Or a parallel flow problem? 8 seconds, 7 seconds. One student's a holdout. I can't help you, buddy. All right. It's counterflow. The cold fluid is flowing this direction, true? And the warm fluid's flowing in that direction. Isn't that counterflow? All right. Next clicker question is the mass flow rate, H. I want to increase it. How would I increase the mass flow rate of the hot fluid? Put a big pump and blow it through. Okay? Think about that conceptually. That should appeal to you. Push a lot of flow of the hot fluid through the heat exchanger. Don't change the hot temperature in. Don't change the cold temperature in. Don't change U. You're saying, wouldn't that have a small effect on you? Say it's a negligible effect on you. And don't change A. Don't make it bigger. Don't change the specific heat of the hot fluid. Don't change the mass flow rate of the cold fluid. And don't change the specific heat of the cold fluid. The only thing you change is the mass flow rate of the hot fluid, right? I have to set this all up. Now we're ready to ask a question. Is how will the hot temperature profile change? Can somebody just tell me that verbally? How, without a clicker? How will the hot temperature profile change? What will it do? That's right. It'll slope. It'll stay pegged right here. The hot in is pegged, but it'll go up. What does the hot out do? Goes up. It increases. The hot outlet temperature will increase. True? All right. Let's do this. Get rid of these. How will TC profile change? Not a clicker question. I have plenty of clicker questions to come. Will it change at all? Maybe I should have asked that question, huh? Well, let me ask this. Is TCN going to change? No. So basically, if you tell me what happens to the temperature cold out, I'll tell you what happens to the profile, right? So does the temperature cold, this is now a clicker question. Does it go up? Answer A. Does it stay roughly the same? Answer B. Not precisely to 8 digits, but essentially the same. Or does it go down? Answer C. 33 seconds. What does the temperature of the cold fluid going out do? All right, we're done. Now, let's say somebody says you're blowing more hot fluid through the system. We realize that the hot out just shifted up. It's flatter up here. We agreed to that, true? That one pretty good. Think about this. What did the delta T log mean for the entire heat exchanger do if the cold would have stayed the same? It would have gone up. True? It's the log mean temperature difference is like some average delta T. Because it went up, isn't it a little greater than just that? Yeah. So what did Q do? The rate of heat transfer do? It went up. It went up. Q overall for the heat exchanger went up. I blew some more hot fluid through it. So what does the temperature cold out do? So it's not easy questions, is it? It's tough questions. Sorry about that, but it's heat exchangers. Heat exchangers are conceptually, I think, challenging, so that's why I'm taking this approach. So what happens? What is the best answer now, knowing that the Q does change? You do have more heat transfer out of the hot, which means it's a greater rate of heat transfer into the cold, and the cold mass flow rate didn't change. So what's happening? It goes up. The smallest percentage. But it's right. True? Yeah. So I know that I should have maybe asked this question first, shouldn't I? Because that's a key. It's like understanding what happened to the log mean temperature difference. Okay, we have more questions. Let's try this problem. Let's take a look at 3 cases, A, B, and C. Answer A, B, or C. And what we have is we have the hot fluid is just flat. The hot fluid's flat, the hot fluid's flat. Okay? But the cold fluid is doing something. It's coming in, it's a counterflow. In the first case A, it goes something like that. Case B, it goes something like that. And case C, it's going something like that. They all have the same inlet temperature of the cold. They all have the same inlet temperature of the hot. Temperature hot in is all the same. All right. Well, we already answered that type of question. So let's take a focus. This first question right here. Forget that one, but this one right here. The hot fluid. Is it condensing or is it evaporating? Answer A if it's condensing, or answer B if it's evaporating. All 3 of these cases, the hot fluid is not changing temperature from in to out. So it's probably doing one of those, right? So what is it doing? What is the hot fluid doing? Is it evaporating or condensing? Yeah, for all of them. Actually, to answer that question, all you have to do is even forget about these for now. Kind of got ahead of myself by sketching those. All right, so the polling has stopped. Is the hot fluid having heat transferred out of it and to the cold fluid? So it's coming out of the hot. So if it's coming out of the hot, it's going to condense. True? It's going to condense. So let's take a look at how we did. It is condensing. Hey, you're pretty good as a class. Not bad. Now I have 3 cases, right? What's really different is what's happening to the cold fluid. For which of these 3 cases is the log mean temperature difference the largest? Which case, A, B, or C, has the largest log mean temperature difference? Somebody asked me, I don't understand. What's the definition of log mean temperature? Okay, it's delta T1 minus delta T2 divided by natural log delta T1 over delta T2. Well, what I encourage you to do maybe sometime, not right now, we don't have enough time, but let's just pick delta T2 as 50 degrees C for all of these cases. 50 degrees C, 50 degrees C right there, right? And then what do you think it is roughly for delta T1 for this case? 50 degrees C. How about for this case? Delta T1. 1 degree C. 1 degree C, okay? How about for this case? Delta T1 is 20 degrees C or something like that, right? And then just run it for those 3 cases. Just run the equation and I think you'll see it. But visibly, which one would give you a larger overall delta T throughout the heat exchanger? This one, case C, wouldn't it? So, but I encourage you to run it with some numbers through that equation because it's hard to see it mathematically, but intuitively, what is it representing? Some mean appropriate temperature difference to drive the heat transfer throughout that heat exchanger. Which case has the largest cap C of the cold fluid? Cap C of the cold fluid. I forgot. What is the name of cap C for the cold fluid? Heat capacity rate for the... I forgot. What is the definition of the heat capacity rate? Product of mass flow rate, specific heat, constant pressure. Well, we're done. Now, let's go back to the hot fluid. How did we get the temperature of the hot fluid to be pretty flat? How did we get that? We had a phase change, which we represent by something with the specific heat during the phase change. The specific heat constant pressure during a phase change, we treat it as being, goes off to infinity. Right? Another way that you can get the hot fluid temperature profile to be nearly flat is to play with MDOT. What would you do to the mass flow rate of the hot fluid to get it to be a nearly flat temperature profile? Jack it way up, pump it, blow it through, right? Same thing applies for the cold. If I want a flat cold profile throughout the heat exchanger, either I blow a lot of cold fluid through, M dot of the cold's high, or it's undergoing a phase change, hence its specific heat constant pressure goes to infinity, right? So both of those will drive the heat capacity rate really, really high, and you have a flat temperature profile. Oh no, what happened? Yeah.
Capital C of H, and that's where I made a mistake.
Okay, capital C of H. All right. Okay. Well, after the explanation, I think you get it right. Let's press forward. This is a very simple question, not a clicker question. Here is the heat exchanger. How can I increase the area of my heat exchanger? You just... How do I increase the area? Make it longer. Make it longer. It used to go from 0 to L. Here, 2L, 3L. You just stick it way out. You just make it longer. That's the easy answer for how you make it increase the area. Without changing the hot temperature in, the cold in, the overall heat transfer coefficient U. Can I increase the area without changing U? The answer is yes. Pretty much yes, okay? Now, the thing is we often have U and A paired up, and they don't really like to be separated, and that's why it makes it a challenging question. But the bottom line is, yes, you can have it. And now you say, but don't I have, maybe I have U based on the outside area and A based on the outside area, and then I have U based on the inside area and A based on the inside. Yeah, there's some fudging on which area, not a fudging, but you have to pick which area that U depends on, especially if one side have a significantly different area than the other side. But if it's a thin-walled tube, negligible conductive resistance, you just have convection on the inside, convection on the outside, they're essentially the same area, then just U depends not on A, it's just the H's. All right. So now let's answer some other questions. Sorry about these questions being so challenging, but let's try this question right here. Let's try this question. So if area is increased by maybe making it longer, how will the temperature of the hot fluid on the outlet change? Will it increase? A, negligible change, or decrease? Temperature hot out. Let me start it. All right, everybody good? Hopefully you're all in. What does the hot fluid do? Yeah, it's as if it was this long, it came out that temperature, right? But if you make it longer, isn't more Q going to happen? Isn't Q larger Q? And so it'll come out here. So the slope changes as well, but it comes out at a lower temperature. Temperature hot out goes down from what it was. All right. So let's go ahead and grade that. Hey, pretty good. Now, let's see which of these. I can't ask them all. Let's ask this one right here, that question. So if area is increased, how will U change? Yep. How will U change? We're done. Well, this was a trick question, wasn't it? Is the answer already explained in this sentence right here? Yeah. It's kind of like, I know it felt bad, but hey. Maybe it was make up for the other tough questions, because most of us got it. Almost everybody. I'm going to skip to the next one. All right, here we have. Somehow, U, how can you change U only without changing the mass flow rates and the heat capacity rate, the specific heats, without changing the area, without changing the inlet temperature? Is there one way to be able to change U? Just somehow change U? No, the fluid's not going to change. So the specific heat of the fluid's not going to change. Some other way. The mass flow rates are fixed by the heat capacity rates being fixed. How can I change U? Fouling will definitely change it. And there's one other mechanism that I'm looking for. It starts with the letter F. 3-letter. Fins. You fin the side. If you fin the side, it essentially helps promote U. All right. Or effective U. Maybe you don't like that. Maybe you think that A would be affected by the finning, but fouling or finning. Let's say that now, let's say the length, this is the length here is not changed, but somehow inside you finned it, and so you increase the overall heat transfer coefficient. So now what we do is we come over here and we're ready for some questions. So if U is increased, without changing all these other parameters, how will T hot out change? I'm kind of bored on that one. How about Q? Let's try this one. How will Q change? If U is increased, everything else remains the same. Think about maybe adding finning inside. This would be like a length, perimeter length calculation for an area. Yes and no. I mean, yes. It's how you look at your internal equation. Well, the time is up. Now I'll try and do a better job of answering that. But let's have a 1 over UA, and let's do it on the outside, okay? And that would be 1 over the H on the inside, area inside. I'm going to neglect wall resistance and fouling, and then I'll have 1 over H on the outside, area outside. But now I want to somehow fin the inside area. Will it change the outside area? So I'm only going to fin the one area that is going to essentially enhance U without the A. I know I'm playing tricky here. It's difficult. But if I wanted to, then I basically get the area on the inside goes up by finning, and then I add an overall efficiency due to the finning on the inside. And that's how I modify it. Okay, so what did we come in for how it affects Q? Yeah, it's going to promote heat transfer. It's going to promote Q. I'm going to move on. This one's a little easier. How can the heat capacity rate of the cold fluid, and only that one, be increased? Pump it. Pump it. Put the mass flow rate up high. You could change also to get a higher specific heat for the same mass flow rate, and that would have the same effect. So let's solve a couple of these. Let's solve which one? This one? There you go. If the heat capacity rate of the cold fluid is increased, how will the temperature of the hot out change? How will this TH out change? All right. So I like that. I can see some people using their hands. So what's going to happen to the blue profile? Won't it go down like that? Yeah. And then what would happen, you open it up, the difference, delta T everywhere through that heat exchanger, a little larger log mean temperature difference, a little larger Q, hence the hot is going to come down a little. The red will come down a little more. True? Yes. That's the right sequence of things. So the temperature hot out will decrease. True? All right. Well, there's a log mean temperature difference. Let me summarize. If I wanted to get the Q, I would have to know UA, how big it is thermally, and then get the log mean temperature difference. What's that average delta T inside? The problem is a lot of times we don't know the temperature cold out and the temperature hot out, yet they're required in the log mean temperature difference. Hence, you're stuck in a loop if you use the log mean temperature difference method. So what they did was they build on the log mean temperature difference method and came up with another method that avoids the requirement that you would need to iterate to converge to a solution that's often encountered in the log mean temperature difference method. So the effectiveness-NTU method, it says, okay, I want to get the rate of heat transfer in a heat exchanger. It's equal to the effectiveness times some absolute maximum. Okay. Well, now I need to define two terms. What is the maximum? Well, the maximum kind of is funny. It's like I have the flow rate of the cold fluid and the flow rate of the hot fluid, and I get the minimum of the two heat capacity rates. And then I think of the maximum temperature hot in minus temperature cold in, the maximum hot temperature minus the maximum or the minimum low temperature. That gives me the maximum delta T, and that's the maximum theoretical Q that could be transferred in that heat exchanger, Q max. Well, what again is C min? C min is just the minimum of either the cold fluid or the hot fluid heat capacity rate. Okay, great. Now, what is this effectiveness? The effectiveness, right? Well, what you would do is you would find it as a function, FCN, of a parameter. It's to be a function of the number of transfer units of that heat exchanger. What is the number of transfer units? The number of transfer units is UA, the thermal size, normalized by the minimum heat capacity rate. So, if you're trying to, what we call rate the heat exchanger, find out the rate of heat transfer occurring in that heat exchanger, what you typically do is you go get the size of it, S-I-Z-E, the area, and then the convection coefficients to get the overall heat transfer coefficient, normalize it in a number of transfer unit, find the right correlation for that heat exchanger so you get the effectiveness. That goes up here, calculate Q max, and that's how you would start with the size and get the rate. Let's say you did the opposite though, because sometimes people want to start with the size and go to the rate. Sometimes you start with the rate that's required and you size it. This is the rating problem, the rate the heat exchanger problem. Here's another problem. It's called the size the heat exchanger, meaning I know what I want to achieve in the Qs. Tell me how big of a heat exchanger I need to buy or spec out in the dimensions. So that it's the same equations, you just turn it around a little bit. So if you still have Q max is equal to C min TH in minus T cold in, all right. And that, you know what Q is, hence you calculate the effectiveness by saying this is what I want to achieve. You divide it by Q max. Then you look for the cousin equation, which is turned around, which says that the number of transfer units is a function of the effectiveness. And there's two sets of these equations in every undergraduate heat transfer book written in the last, I don't know how many years, where they say, oh, if you give me the NTU, I'll give you the effectiveness for this type of heat exchanger. Or if you give me the effectiveness, I'll give you the NTU for that type of heat exchanger. So once I get that, then I unravel to get A, is because remember, number of transfer units is UA over C min. I get the number of transfer units, multiply that by C min, divide by U. I've now sized my heat exchanger, how big physically it needs to be. So the effectiveness-NTU method uses a lot of relationships. Here's a table out of our textbook. Here is the effectiveness, 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 and on the right-hand side, there's an equation with NTU embedded in it. Okay, here it's a little cumbersome. Some people, you can tell, did a lot of work to develop these relationships. And then if you look, I think 11.4 gives you the flip side, the NTUs as a function of the effectiveness. I'm out of time. Sorry that I ran a little over. I have to stop right here. I just noticed that. Thank you very much. Have a safe, wonderful weekend.